Partial fraction decomposition. Let's go ahead and start by reviewing how to add two rational expressions. So I have 2 over the quantity x plus 1 plus 3 over the quantity x minus 4. To proceed, we're going to need to find the common denominator, which is just the quantity x plus 1 times the quantity x minus 4. So our first fraction is going to be 2 over the quantity x plus 1, and if I multiply the bottom by the quantity x minus 4, I also have to multiply by that on the top. And then we have plus the right fraction, which was 3 over quantity x minus 4. We'll have to multiply the top and bottom by the quantity x plus 1. So now that they have common denominators, I can go ahead and add across the numerator. So I'll have to distribute. I'll have 2x minus 8 plus 3x plus 3 all over the common denominator of x plus 1 times x minus 4. So I end up with, in the numerator, combining like terms, 5x minus 5 all over. On the bottom, if I multiply out those two binomials, I'll get x squared minus 3x minus 4. So we started with 2 over the quantity x plus 1 plus 3 over the quantity x minus 4, and combining those together we got quantity 5x minus 5 all over x squared minus 3x minus 4. So this means that 2 over x plus 1 plus 3 over x minus 4 is the partial fraction decomposition of 5x minus 5 all over x squared minus 3x minus 4. What we're interested in doing is the reverse procedure of what we just did. The reverse procedure of starting with a rational expression and writing it as a sum of two or more fractions with, quote, simpler denominators is called partial fraction decomposition. And the two or more fractions are called partial fractions. So in this section, we're going to be given one rational expression, and in this example, my denominator is a quadratic, and we want to break it down, right, decompose it into the sum of two or more simpler denominator fractions. So these are linear denominators instead of a quadratic denominator. A quick note before we start: to find a partial fraction decomposition, we need a proper rational function. A proper rational function, p of x over q of x, where q of x does not equal 0, has polynomials with degree of p of x, so the degree in the numerator, is less than the degree of the denominator. So if the degree of p of x, the numerator, happens to be greater than or equal to the degree of the denominator q of x, we have an improper rational function, and we must first perform long division. Let's jump into our first example. We want to find the partial fraction decomposition for 3x minus 4 all over x squared minus 2x minus 3. I'm going to start by rewriting the rational expression 3x minus 4 over x squared minus 2x minus 3. And the next step is going to be to factor the denominator if it isn't already factored. So here my denominator is going to factor to x minus 3, x plus 1. So now each of those linear pieces, x minus 3 and then x plus 1, those are going to be the denominators of my partial fractions. So this quotient, this rational function, is going to equal some number, let's call it a, over the linear factor x minus 3 plus some other number b over the linear factor x plus 1. So our job is to find these numerators a and b, these constant terms. Well, the whole idea is that when we add these back together, they should give us our original rational expression. So we're going to go ahead and think about adding these generic pieces back together now. Well, to add it back together, we're going to have that common denominator of x minus 3 times x plus 1, and the a on the top would need to get multiplied by the x plus 1, so we'd have a times the quantity x plus 1, and then the numerator constant b would have to get multiplied by x minus 3, so we have plus b times x minus 3. So again, we're in search of these values a and b, and it has to be true here. We can kind of follow the string of equalities. The denominators are the same, quantity x minus 3, quantity x plus 1. So if we really want these to be equal, we're essentially setting their numerators equal to each other. We want to know what values make 3x minus 4 equal to this a times quantity x plus 1 plus b times quantity x minus 3 scenario. I'm going to go ahead and set the 3x minus 4 equal to a times the quantity x plus 1 plus b times the quantity x minus 3. So now the only way these two can be equal to one another is if we compare all the terms in front of x, and those are all equal to one another. So in other words, on the left-hand side of the equation, I have just a 3 in front of the number x. And on the right-hand side, if I think about distributing in the a, I would have an a in front of x, and then if I distribute the b in, I would have a b in front of x. So here's what I'm going to do to kind of organize my work. I'm going to think about, okay, well, in front of the x terms, so I'm thinking about in front of the x terms, I have a 3. Well, that would have to equal a plus b. So the stuff in front of x on the left would have to equal the stuff in front of x on the right if the left side is truly equal to the right side. And then the constant terms on each side, so on the left side, the constant term, the one without any x's involved at all, is negative 4. And negative 4 would have to equal the constant terms on the right-hand side. Well, the constant terms on the right-hand side are going to be a, because after I distribute the a into each side, I'll have an a there. And then after I distribute the b into both sides, I'll have a minus 3b. So those are going to be all the terms that don't have x's involved. So I'm going to have the constant terms. So I'm going to go ahead and, again, organize my work. The constant terms on the left, negative 4, would have to equal, on the right, a, and then minus 3b. So the stuff that doesn't have any x's associated with it. So after I distribute in the b, negative 3b won't have an x associated with it. After I distribute in the a won't have any x's associated with it. So what I've essentially created here is a system of equations. So I have two variables with two unknowns. I have 3 equals a plus b, and negative 4 equals a minus 3b. So now I have either substitution or elimination that I can use to solve this system of equations. I'm going to choose elimination. I'm going to multiply this top equation by a positive 3 so that when I add it to this bottom equation, it will cancel out my b terms. So here I'm going to go ahead and multiply by positive 3. So my new top equation is going to be 9 equals 3a plus 3b. My bottom equation is still negative 4 equals a minus 3b. So when I add these together, I'm going to have 5 is equal to 4a. And then I'm interested in solving for a and b. That's the whole point, solve for a and b, because we want that decomposed, or those decomposed fractions, the smaller fraction, or simpler fractions. So I'm going to find a by dividing by 4. So I'm going to have 5 over 4 is equal to a. And then I can substitute a into any equation involving a and b. So I'm going to go ahead and substitute 5 over 4 into 3 equals a plus b, that just original equation. So I'll have 3 is equal to 5 over 4 plus b, and I'm going to solve for b. So I have 3, which I'm going to rewrite as 12 over 4, minus 5 over 4 is equal to b. So b is 7 over 4. So what does that mean? My partial fraction decomposition, I was in search of these values a and b, and I just found them. So my partial fraction decomposition is going to be a over x minus 3, so we have 5 over 4 over x minus 3 plus 7 over 4 over x plus 1. But in this case, I don't want to leave a complex fraction, a fraction inside a fraction, so those denominators of 4 are going in the numerator are going to move down to the overall denominator. So it's going to look like 5 over 4 times the quantity x minus 3 plus 7 over 4 times the quantity x plus 1. So this is my partial fraction decomposition. So if we were to add this back together, we would get our original rational expression. Alright, before we move on from this example, I'm going to go over an alternate way to find the values of a and b. So we're still going to work with the idea that 3x minus 4 has to equal the a times x plus 1 plus b times the quantity x minus 3. So we're still going to work with that equation, and we're still trying to find a and b. But instead of solving a system of equations where I set all the stuff in front of x on each side equal to each other, and all the constants, the things that don't have anything to do with x on both sides, equal to each other, we are going to strategically pick x values. So what we're going to go ahead and do is if the left side truly equals the right side, which is what we're operating under, then it should hold no matter what x value we pick. So what we're going to go ahead and do is we are going to choose the x values that will eliminate an entire term on the right hand side if possible, because then that will eliminate either a or b. So focusing in on a times the quantity x plus 1, if I conveniently choose x to be -1, -1 plus 1 will be 0, and that will eliminate my a term. So what I'm going to do is I'm going to start by letting x equal -1. And that's for every x. So the left-hand side becomes 3 times -1 minus 4 equals 0. That's the whole point. That right-hand side, one of those terms should 0 out. And then I have just b times -1 minus 3. So on the left, I have -7. On the right, I have -4b. Well, that means I can just go ahead and divide by -4, so I get the value of b is 7/4, which we already knew from solving a system of equations. Now, to find the value of a, we can go back to this original equation and again conveniently choose, so here's my original equation, we can conveniently choose a value that will eliminate the b variable term. Well, that would be a +3. 3 minus 3 is 0, so that will cancel out the right term. So we're going to go ahead and let x equal 3. Now I have 3 times 3 minus 4 equals a times 3 plus 1, and then plus 0. And so what we have on the left is 9 minus 4, which is 5, equals 4a. And then dividing both sides by 4, I get a is equal to 5/4. So we do get the same exact partial fraction decomposition. 5/4 was a, so that goes on top of x minus 3. It's important to keep the same variable, depending on how you labeled it, above the correct denominator. So simplified, we'd have 5 over 4 times the quantity x minus 3 plus 7 over 4 times the quantity x plus 1. So the same answer, but an alternate method. Now my only warning is that while this is simpler, it doesn't always work out. The solving the system of equations method will always work. It just may be more time consuming, and it may be best to do a combination of those two things, as we'll see with further examples. All right, so this now goes through a little bit of the process of finding a partial fraction decomposition for some rational expression, f of x over g of x. So this assumes that we have a proper rational function, and then first we must factor the denominator, and then depending on the factorization of the denominator, we're going to get different partial fractions. So if we get a distinct linear factor, distinct meaning different, if we get different linear factors, ax plus b, then we're going to have a corresponding partial fraction, some constant, a1 over ax plus b, for every distinct or different linear term. That's like the example we just did. We got two different pieces in the denominator, two different factors, so we put a, some constant, above one of them, and b, some other constant above the other one. But there's different possibilities. So what if we get what's called a repeated linear factor? So we get ax plus b to the kth power. Well, then what's going to happen is we're going to have multiple partial fractions. So we're going to need a different constant over the linear factor to the first power, plus a different constant over the linear function to the second power, and we just keep going with this until we get to whatever power it happens to be. So we'll see examples of this because it looks a little more intimidating than it really is. And the other possibility is we don't always get linear factors. We can get irreducible quadratic factors. So quadratics that we can't factor, ax squared plus bx plus c. If that happens, our partial fractions will look like the quadratic, the irreducible quadratic on the bottom, and instead of a constant on the top, we have a linear function on the top. And if we get a repeated irreducible quadratic, then we have those repeated linear over irreducible quadratic up until we get to the power of the irreducible quadratic form. So the big picture here, the big concept behind this page that looks a little intimidating is that if we have a linear term on the bottom, what has to go on top of it is a constant, right? Just one single variable, a number. If we have an irreducible quadratic on the bottom, then what goes on top of it is a generic linear function. So we would have a generic linear function ax plus b, right? So we should know that's a linear type of function. And from there, once we have everything set up, then we're going to have to set up and solve that system of equations to find the missing variables. Let's take a look at another example. We're going to find the partial fraction decomposition for x squared minus x minus 21 all over 2x cubed minus x squared plus 8x minus 4. The first thing we need to do is factor the denominator. So I'm going to do that scratch work sort of off to the side here. So I have 2x cubed minus x squared plus 8x minus 4. And because I have 4 terms here, I'm thinking that I should try factor by grouping. So within the first 2 terms, I can factor out an x squared, and I'm left with 2x minus 1. Between the second 2 terms, I can factor out a positive 4, and I'm left with that 2x minus 1. So that quantity 2x minus 1 is in common in both terms now. So if I factor that out, 2x minus 1, I'm left with x squared plus 4. Well, x squared plus 4 is an irreducible quadratic. I cannot factor it any further. So this is my denominator factored. So my original rational function would look like x squared minus x minus 21 over this linear term, 2x minus 1, times this irreducible quadratic, x squared plus 4. So to set up our partial fraction decomposition, what we need to know is that the linear factor in the denominator gets a generic constant on top. So we'll call that a. And the irreducible quadratic term gets a separate fraction, but above it goes a generic linear term. So a linear term in general, I'm going to call bx plus c. So I'm just continuing to use the letters alphabetically. So I used a first, then my next generic constant was b for the slope of my generic linear term, and then c would be like the y-intercept of my generic linear term. So I'm ultimately solving for a, b, and c. I'm missing all of those constants because I want to complete this partial fraction decomposition. I've created two fractions, but it's missing those values. So what we do is, well, we think about if these two fractions are truly going to equal this one quantity, I should be able to put them back together. Well, if I put them back together, they will have that one common denominator, 2x minus 1 times x squared plus 4. And on the left side, a will get multiplied by x squared plus 4. And on the right side, bx plus c, that entire factor, so I'm going to put it in parentheses, bx plus c would have to get multiplied by 2x minus 1. So 2x minus 1. So now, the numerator, x squared minus x minus 21, that original numerator, will have to equal the a times quantity x squared plus 4 plus quantity bx plus c times quantity 2x minus 1. So that's what I'm going to look at. I want to set those equal to each other to solve for a, b, and c. So I want x squared minus x minus 21 equal to a times quantity x squared plus 4 plus, and then we have bx plus c times quantity 2x minus 1. Now, if we were thinking about trying to maybe use that shortcut method and pick a convenient x that will eliminate maybe this whole first term, if I try to plug something into this x squared plus 4, and try to make it equal 0, there's no real solution to that, because if I take any number and square it, I'm making it positive, and then I'm adding 4, so there's no way that that's going to be equal to 0 ever. Now, we could try it for this second piece over here, so we could go ahead and find a value that makes 2x minus 1 equal 0, so that would actually be positive 1/2, but then the whole thing is that that's supposed to make the problem quicker, and it's not going to make the problem quicker if we have to plug in 1/2 into every x. So here I have 1/2 squared minus 1/2. I'd have to plug in 1/2 here. So it wouldn't really make it a lot simpler. We're still going to have to solve a system of equations anyways. So that isn't the best route here. So we're going to go for setting up that system of equations. And this time on the left-hand side, I have a x squared term, an x term, and a constant term. So what I have to do is I have to think about the coefficient in front of the x squared term on the left, and then what would all the coefficients that are in front of x squared on the right-hand side look like. So here I'm going to again sort of organize my work and think about it as, all right, what's in front of x squared? Well, on the left there's a 1 in front of x squared, and that has to equal all the stuff on the right that's in front of x squared. Now, best case scenario is that we can do this mentally, as we did on the previous one, but if you have to, you can multiply it out to really see all the stuff that's in front of x squared. So let's try to do it first without multiplying it all out, but then I will multiply it all out. So here, if I did distribute in this a, in front of x squared would be a, and then over here on the right hand side I'd have to distribute all this, so bx times 2x would create a 2bx squared, and then my outer would be minus bx, and my inner would be plus 2cx, and my last would be minus c. So the only thing that's going to give me an x squared term is the bx times 2x. So I'd have a 2b in front of x squared, so plus 2b. Now again, I said it all and we'd want to try to mentally think about it, but if you really have to, you can distribute. So you can say this would be ax squared plus 4a plus, this was 2bx squared. Outer would be minus bx, inner would be plus 2cx minus c. So we could just multiply it all out. And now, in front of the x term, so it's like we're done with x squared, now we move on to the x term. Well, if the left side equals the right side, all the stuff in front of x on the left should equal all the stuff in front of x on the right. So in terms of the x term, on the left-hand side, we have a -1 is in front of x. On the right-hand side, well, this was an x squared term. This is a constant. It has no x's. 2bx squared. Now, -bx plus 2cx. So in front of the x terms, I have a -b and a plus 2c. So I have -b and then a plus 2c. And then finally, we're going to go ahead and take a look at the constant terms. So now the ones without any x's. So the constant on the left-hand side is -21. And that's going to have to equal all the terms without any x's on the right. So that's going to be 4a. And then just minus c. So now here is our system of 3 equations with 3 unknowns. We wanted a, b, and c. So these are my 3 equations. And we're not going to have enough space right here, so I'm going to have to clear some space. Alright, so now here we go. There's a lot of different ways to solve systems of equations. What I'm going to go ahead and do here is I'm going to try to create a system of 2 equations with 2 unknowns. So I have this top equation here. It looks really easy for me to isolate a. I can just subtract 2b to the other side. So I'm going to go ahead and write a is equal to 1 minus 2b. And if I now take that a equals 1 minus 2b and I substitute it in to, this a right here in the bottom equation, then the bottom equation will have b and c in it. And this middle equation already has b and c in it, so I'll be able to solve those 2 equations. So I'm going to go ahead and leave the middle equation alone for now. And again, I'm going to substitute my 1 minus 2b into this a right here. So then my bottom equation is going to become -21 equals 4 times 1 minus 2b minus c. So -21 equals 4 minus 8b minus c. I'm going to subtract the 4 to the other side, so -25 equals -8b minus c. So that's my new bottom equation, right, after that substitution was made right there. And so now I'm going to go ahead and use that middle equation, and I'm going to put -1 equals -b plus 2c. So this is my little smaller system of equations now that just involve b and c. So now to solve this system of equations, I'm going to multiply the top equation by a positive 2 to cancel out this c right here, plus 2c. This will be a minus 2c if I multiply that top by a positive 2. So here I'm going to multiply by a positive 2. I'll get -50 equals -16b minus 2c. And the bottom equation was the same, -51 equals -b plus 2c. Now it looks ugly, but nice stuff's going to happen right now. When I add down, I get -51 equals -17b, and that's it because the -2c and the plus 2c cancel. And -17 goes into -51 3 times. So the value of b is 3. And now I can take that value of b being 3 and plug it in to find a, because a was 1 minus 2b. And I can also plug it into this original middle equation, plug in b to find c. So let's go ahead and find a first, just because that one looks a little bit easier. So now a is 1 minus 2 times 3. So 1 minus 6. So a is -5. And then I had 1 was equal to -b plus 2c. So -1 was equal to -b. We found out that b was 3. Plus 2c. So if I add the 3 to the other side, I'm going to get positive 2 equals 2c. So divide both sides by 2, I get c equals 1. So now that we have the values of a, b, and c, we can substitute it into our original partial fraction decomposition setup, which I'm going to copy back down for us. So we originally had, it was a over 2x minus 1, and then plus bx plus c over x squared minus 4. So it's now just replacing those values of a, b, and c. So a was -5, b was +3, and c is 1. So this is my partial fraction decomposition. In this next example, we're asked to set up but do not solve for the following partial fraction decomposition for 3x minus 5 over x cubed minus 1. So first thing is I need to factor x cubed minus 1. And x cubed minus 1 is x cubed minus 1 cubed, which means this is the difference of cubes. So we have to remember the difference of cubes factorization formula, which is subtracting, so we keep the same sign. We're taking x minus 1, and then we do the first term squared, so that's x squared. Then we do the opposite sign, so we had minus, now it's plus. And then we just multiplied the two insides together, so x times 1 is x. And then the last part's always positive, and then we take that last number and square it. So 1 squared is 1. So here we have factored the denominator, so our original rational expression is 3x minus 5 over the linear term x minus 1, and the irreducible quadratic x squared plus x plus 1. So this x squared plus x plus 1, it cannot be factored, so it's an irreducible quadratic. Now all we're doing is setting it up, and so it's the idea that the linear term x minus 1 would create one partial fraction with a constant above it, and the irreducible quadratic x squared plus x plus 1 would create another term with a generic linear term on top, my bx plus c. So for this problem, that's all we're being asked to do. Set up, but don't solve completely for the following partial fraction decomposition.